Welcome to my second lecture in the seminar Geometric Analysis Past, Present and Future. I'm Tyrrell and I'm talking about renormalized area for minimal hypersurfaces of five-dimensional Poincare-Einstein spaces. So we've seen in the last class what we mean by a Poincare-Einstein space roughly and how we come to those ideas. I just want to go over the background more carefully now from the point of view of kind of starting with some Poincare-Einstein space. So we suppose that we have a complete Riemannian metric G plus on the interior of a compact manifold with boundary. So the compact manifold with boundary is X bar. This metric is said to be conformally compact if we can extend it to this metric G bar by compactifying it by multiplying by this R squared. And you can kind of think of R as kind of acting like a distance to the boundary function. Right? It's not really that, but sometimes it is locally that. With respect to this G bar. So if this extends to a metric on the entire compact manifold, where R is a defining function for the boundary, which we call M, and by a defining function we mean this. So R is positive on the inside of X, R is 0 on the boundary, and dr is never 0 on the boundary. So then that's what it means for a manifold to be conformally compact, or a complete Riemannian manifold to be conformally compact like that. Now, we call this equivalence class of G plus sub infinity, and that's defined to be the conformal class of the compactified metric G restricted to the boundary. We call that the conformal infinity of Xg plus. So that's basically just if you take your metric compactified restricted to the boundary, look at that conformal class. That's the conformal infinity of G plus. And this is a well-defined invariant of G plus, clearly. And then a slightly less obvious invariant of G plus is the following. If you take the differential of R and you take its norm squared with respect to G bar, where G bar means compactify G plus with R, if you take that restricted to the boundary, this actually doesn't depend on the defining function that you chose. So that's a very nice fact. And in fact, conformally transforming the Riemann tensor of G plus gives you this for the components. And this term goes to 0 as you approach the boundary. So this says that the sectional curvature, so this Riemannian curvature approaches the curvature tensor for a constant curvature metric as you go towards the boundary. So this implies the sectional curvature approaches minus the norm squared of dr with respect to G bar as P approaches M. So now we're just going to talk about another definition. So asymptotically hyperbolic manifolds are conformally compact manifolds that have asymptotically sectional curvatures equal to -1. So if this was -1, so if this was just 1 on M, then it would be an asymptotically hyperbolic manifold. But right, so now this is a special definition as well. A special defining function for M is a defining function R such that dr squared with respect to G bar is identically 1 in a neighbourhood of M. So rather than just on M itself, so you can think about that as there's some neighbourhood. So if this is M, the inside is X, say, and say we can take some neighbourhood of M. So we should call that a collar neighbourhood. And if in here dr has length 1, so in there dr basically acts like a distance to the boundary function with respect to G bar. So it's a lemma in a paper of Grab's that for every metric H in a conformal infinity of an asymptotically hyperbolic metric G plus, there's a special defining function R such that when you compactify by that defining function, special defining function, you'll get H. So a choice of special defining function corresponds to a choice of representative for the conformal infinity of G plus. So a conformally compact manifold that also satisfies this particular Einstein condition, this is one we talked about before in the last lecture, is called Poincare-Einstein. So it's a Poincare metric for your boundary metric. For such a manifold, it can be checked that this will be equal to 1. So if you're Poincare-Einstein, you can actually check that this is going to equal 1. And you can check that by going back here and looking at this equation. So it follows the Poincare-Einstein manifolds are special cases of asymptotically hyperbolic manifolds. So now a defining function. So if I draw this picture again, a defining function determines for some epsilon an identification of this collar neighborhood with a neighborhood of M in X bar. So basically determines a diffeomorphism of some collar neighborhood of the boundary in X with just M cross an interval. So, and with respect to this decomposition, we can decompose in terms of these variables then. So we can decompose the metric in terms of R and then the coordinates that are perpendicular to R if we have a special defining function. And then the metric takes this form in those coordinates. G bar will be GR plus DR squared, where GR is a one parameter family of metrics on M. So using the Einstein condition, you can actually compute what's known as the Pfefferman-Graham expansion for GR. So this is related to what we talked about before in the work by Pfefferman and Graham. This metric, you can actually use the Einstein condition to find some of its derivatives on the boundary. So when n plus 1 is even, this will actually take the form of this, where the GIs are formally determined up as far as n minus 1. And then the next one is trace-free with respect to any metric in the conformal affinity. So Graham showed in a paper that he wrote in 1999 that using the terms in the Pfefferman-Graham expansion, you can actually write down an expression for the volume form of the Poincare-Einstein manifold. And using that, you can actually show that what's known as the renormalized volume doesn't depend on the choice of special defining function. So what we mean by renormalized volume is, right, so if this is your Poincare-Einstein manifold, if you, so say this is X, if you pick some epsilon, which is a kind of a distance to the boundary with respect to G plus, and you just call all of the points that are more, if you take the set, so X epsilon, so X epsilon is just defined to be X intersect R greater than epsilon. If you compute the volume of this with respect to G plus, this would be some finite number. But the volume of X itself would be infinite because G plus is complete. So if you expand this in terms of epsilon, I should get like epsilon minus n or something, and then you'll get some finite or some zeroth level term, and then higher order terms. This zeroth order term is what's known as the renormalized volume. And all these other terms depend on the choice of special defining function. You can see that this construction clearly depends on the choice of special defining function because even X epsilon is defined in terms of R. But this renormalized volume will not depend on R when X is even dimensional. And there's work by Anderson then. He obtained a Gauss-Bonnet formula that encompasses the renormalized volume. Right, so on a Poincare-Einstein manifold of of dimension 4, we get this Gauss-Bonnet type formula. This is the Weyl tensor, and the norm squared of the Weyl tensor is a pointwise conformal invariant of weight minus 4. So it actually, when you do a conformal change, it cancels out with the conformal factor you pick up from the volume form. So this integral is actually what's known as a conformal integral invariant. So this integral doesn't depend on, this only depends on the conformal class of G+. And then this is just a topological term. So these are both finite. So then this is a nice formula involving V. So this renormalized volume V, it's hard to get your hands on because it's a global invariant of G+. But in this case, this is a nice formula that encodes it. There's also a nice rigidity result that comes with this. So if you just look at this for a minute, you can see that you can write down the following inequality. And you get equality if and only if the Weyl tensor vanishes. And for a Poincare-Einstein manifold, the Weyl tensor actually, its components actually just measure the failure of the Riemann tensor to be constant curvature, basically. So if this is 0, so we get equality here if and only if this is 0, which is equivalent to G plus having constant curvature. So that's why it's equality if and only if G plus is hyperbolic. It's a nice rigidity result. And so in 1999 as well, Graham and Witten wrote a paper where they outlined an analogous theory for renormalized volume, but for certain minimal submanifolds of Poincare-Einstein spaces. So they looked at Poincare-Einstein space and then minimal submanifolds that extend to the boundary. So Y, K plus 1. And they showed that you can define renormalized area for these things. And if Y is even dimensional, then this renormalized area is an invariant. And Alex Axe and Mazzeo in 2008, they wrote a paper on renormalized area for hypersurfaces in three-dimensional Poincare-Einstein manifolds. And they do a lot more of this paper than just write down this formula. They study its functional properties. But this is a formula they obtained for the renormalized area in that case. So now, time to state the result, or the results from my paper. So here we look at a five-dimensional Poincare-Einstein space, and we take a minimal hypersurface extending to the boundary under compactification, and let AY be the renormalized area of Y. Then you can write this formula for the renormalized area, where E is the trace-free Ricci tensor, W is the Weyl tensor on Y, and B is the second fundamental form on Y. And now this quantity here means the finite part of this, in terms of Y sub epsilon, just means, so that Y sub epsilon just means Y intersect R greater than epsilon. Right, so this integral can be expanded in terms of epsilon, and if you take the finite part of that, which is just the constant term in that expansion, you can write this. So this is not a completely satisfying formula because you have this finite part here, which is difficult to deal with. But we have the following. So if we take the exact same setup as before, then it turns out that this quantity is finite, right? So either of these terms on their own, integrated over the manifold Y, would blow up in general. But together, they're finite. And furthermore, if we can look at the expansion for this guy, and we get that it has an epsilon to the minus 1 term, which is the total integral of the norm squared of the trace-free second fundamental form on the boundary of Y. So that's the second fundamental form of the boundary of Y within the boundary of X. So in that sense. And then the zeroth level term is this. The zeroth order term is this, and then plus higher order terms. So that then allows us to write the following. Right, the formula before that involved the finite part of this L2 norm for the second fundamental form can actually be written like this, which is very nice because now these are all just integrals on y of certain quantities that are understood. And a nice corollary is that the boundary of y is umbilic within the ambient boundary if and only if this integral vanishes. Otherwise it diverges. The way to see that is, well, if this vanishes, well, we can see it from this equation. So if the integral of the Laplacian of the norm squared of b vanishes, then we get this on this side and we have this here. So it must be that the integral of the norm squared of b converges, and then this would have to be 0, which would mean that the boundary of y is umbilic in the boundary of x. And then the reverse is also easily seen to be true. So now here's a sketch of the proof of the formula. So we start off with the Chern-Gauss-Bonnet formula for 4 manifolds with boundary, which can be written like this. Right, so here, this is y bar means the compactified y. So you pick a special defining function. And we get this. Sigma 2 of this means the second symmetric function of this endomorphism. And this endomorphism is just the endomorphism we get by raising an index on the Schouten tensor, which is this. And then these boundary terms SR are just given by this. So it's not too important to see exactly what that is, but it just involves the curvature of the boundary of y, which I also call sigma epsilon. That's the boundary of y epsilon. So this is terms basically involving the second fundamental form and the mean curvature of sigma epsilon within y epsilon. And now you can actually, after a computation, it's quite a long computation, but you can arrive at this. So you can rewrite this compactified sigma 2 like this, plus the divergence of some vector field with respect to h bar. And then, using the following equations, we can rewrite some terms. And we get this is equal to this. And now this 6 here is going to be how we'll pick up the area. So when we plug that in, so this is equal to this, which is actually equal to, so once we rewrite this like this, we get this formula. And we have this divergence here. So applying Stokes' theorem gives the following. So we have this, and then plus some boundary terms. And now if we make a particular choice of special defining function, namely we can choose our special defining function so that the boundary of y is minimal within the boundary of x. That's actually a choice that we can make, and it just corresponds to the existence of a solution of a particular differential equation, which is easy to see that it exists. And then if you make that choice, it makes the calculations easier. And then you can see that the boundary terms here won't contribute to the finite part of this overall expression. So we can forget those when we're just looking for the finite part, because all we're interested in is the finite part of this, because that will be the renormalized area. So then what we get is the following. So yeah, the Weil term, the trace-free Ricci term, and B4, these are all pointwise conformative variants of weight minus 4. So these integrals all converge. So then we're just left with this finite part of this term. But then we can find that this is equal to this. And once we do that, we sub it in there and we arrive at our formula. So this just involves a computation to check. And then that completes the sketch of the proof. So thanks very much, and I hope you found this interesting, and I hope some people have some questions for me in the Q&A session. So once again, thank you to the organisers, and I'll see you all in the Q&A session.